All right, so I said to go over a video with these exceeding problems. For this one here, um, the algebraically, I'll show you. Then I'll kind of talk about it a little bit. But when it says explain in your own words, a lot of you didn't really, you only did one or the other. Some of you tried to explain it, but didn't show me algebraically. Some of you showed me algebraically, but didn't explain it. So make sure that you are answering all parts of these questions. So prove that 0.9 repeating is actually equal to 1. What I wanted you to try and do is think about what we were doing. All in the second half of this test, we were converting repeating or non-repeating decimals into a fraction. So I was hoping that you'd say, oh, okay, so based on what we were doing, let me turn this into a fraction and see if it does equal 1. So we would then say, well, 0.9 repeating. Well, first we see the whole thing's repeating, so I need to multiply it and to bring the repeating part out. So that means I just need to multiply it by 10 because it's the 10th place that it's starting to repeat. So I know that that is 9.9 repeating. Remember, what we did is we can say x is equal to 0.9 repeating. We multiplied it by 10, so now we have 10x. And then we need to subtract the repeating part out of that manipulation we just did to get rid of all those decimals. Our goal is to get it as a whole number. So I'm going to subtract 0.9 repeating the original number that we started with, which we know is x. So I'm doing minus x over here. So now this is going to cancel out all of our decimals, and 9 minus 0 is 9, and 10x minus x is 9x, and that tells us what we're going to end up dividing by. So we're combining these two into one fraction, and we get 9 over 9, which is equal to 1. So that is showing it algebraically. So I was hoping that you would take what we were just doing, and in order to show that this repeating decimal is in fact equal to 1, you needed to convert it into a fraction and see, does it equal 1? And then from here, I want you to just try and explain this in your own words and maybe why this makes sense. So if 0.99999 repeating, that's what that's telling us, that this 9 is going on forever and ever and never ever stopping. Well, is in order, one of the things you can think about that if these aren't the same number, then some number needs to appear in between them. And if this 9 is repeating on and never ending, well, there's no number that's going to be in between them, which is then telling us that they are, in fact, the same number. One of the other ways that you can kind of think about this as well with talking about it, going back to that last one. So if we were to try and draw these like on a number line, there wouldn't be a number that like we can write between 0.9 and 1, we can include 0.95. So if these two numbers weren't in fact the same, then there must be a number that we can write in between them. And if this is 0.9 repeating and here's 1, it's impossible for me to actually put any number in between them since this 0.9 is going on and on and on. So that's actually telling me that they have to be the same number, because if they weren't, we'd be able to put a number in between them like we can with every other number. Another way that you can think about this, and this is something that we're going to use later on, like this intuitive, hopefully it's intuitive, method of coming up with rules, is if we have 1/3, we know 1/3 is equal to 0.3 repeating. Well, 2/3 is equal to 0.6 repeating. And if we kind of continue the same step, we're adding 1 to our numerator each time. So if we do that again, well, that's 3 over 3. And here we see it was going by 0.3 each time, so 0.9 repeating, which we know this is equal to 1. So there's kind of some ways I was hoping that you would just try to explain why you thought this was true, as well as showing it algebraically. All right, so now we're going to focus on the second problem. So I'm going to write it just a little bit bigger here. And there's just a huge difference between the way that the first number is written and the way that the second number is written. And even this third one, but we see these 3s for both of these. This written really big out front, and especially me putting it in parentheses, but even if I didn't, if I just wrote it really big out front like this, well, this is saying 3 times the square root of 64. Where when we write that little 3 on the inside of that radical symbol, that's saying the cubed root of it. All right, so we're just going to go through this problem here. So first off, this one, the square root of 64, well, what number times itself twice is equal to 64? And that is 8. So the square root of 64 is equal to 8. So we know that this is now 3 times 8, which is then going to give me 24. And then here it's saying the cubed root of 55. So we were approximating this. So on your little cheat sheet that you got, you should have extended it to our x cubed. So we have 2, 3, 4. Well, x squared is 4. X cubed is 8. 3 squared is 9, and 3 cubed is 27. Because what this is saying, when we see that x and that power 3, that's saying this is equal to 3 times 3 times 3. So the power is telling me how many times I multiply that base together. So it's 3 3's being multiplied, which is 27. And then our next number for 4, well, we know 4 squared is 16. 4 squared 16, and then 4 cubed, well, remember this is 4 times 4 times 4, which is then going to give me 64. So now from here, as I'm looking, I see now that I'm looking for the cubed root of 55. Well, 55 falls in between these two numbers, and 55 is a lot closer to 64. It's only here, 9 away, where here it is 28 away. So I'm just going to approximate it then without doing much of the work, and I'm just going to say that this is closer to 4, but not quite there. So I'm just going to say 3.8. So plus 3.8. I'll keep the plus 3.8 here. We're just approximating, and I would be even more lenient with these ones than I would for some of the other ones that we had as well, because this is taking what we've learned and kind of applying it in a different way. And now here it says the fourth root. So now this is saying what number is being raised to the fourth power multiplied by itself 4 times is equal to 24. So I'm going to extend this table out one more time. And now 2 to the fourth power. This is saying 2 times 2 times 2 times 2, which is 16. And 24 is above that 16, so I know I had to do at least the next one. And 3 to the fourth power, so 3 to the fourth is equal to 3 times 3 times 3 times 3. Well, each pair of 3 is 9. 9 times 9 is 81, so this is equal to 81. So once again, as for the other one, I gave these ones specifically to where it should have been a little close for you to be able to just make a quick approximation. So 24 is between 16 and 81, and it's a lot closer to 16. So maybe I would say 2.1 maybe, or 2.2, somewhere around there. But I'm just going to say 2.1 because it's a lot closer to 16 than it is to 81. Now that we approximated each of these and I took the square root and multiplied, now we just need to add. So it becomes 24 plus 3.8 plus 2.1. So we're just going to add this down. Well, this is going to give me 0.9. 4 plus 3 is 7, plus 2 is 9. So 29.9 approximately is what the answer should have been. Now, for different tests, you might have had a slightly different problem, but it's the same thought process, and they're very similar in the types of numbers I chose.